In this lesson, we're going to be looking at consequences of the second law, and in particular, how that impacts calculation of entropy change. So, entropy is defined by an imaginary process, but it applies to real and imaginary reversible processes because it's a property. So, it's defined as dq over t for a reversible process. There is not a 0 point that is well defined here, but as long as we're doing changes in entropy, that's not a problem. So in a reversible process, what we do is we go back to our ideal cycle, the Carnot cycle. So we have 2 reversible isotherms and 2 reversible adiabats. Now, they are reversible, okay, so the dq over t is going to be equal to ds. Just simply it is because it's reversible. For the adiabat, dq is 0, right? There's no heat transfer if it's adiabatic. So therefore, delta S is going to be 0. So whenever you see something that's reversible and it's adiabatic, it means that delta S is 0, or the entropy is constant, or isentropic. There's that same root word again, that iso, or isa. Now on the isotherms that are reversible, dq over t, well the t is constant, and so I can pull it out of the integral. And so I just end up with the net heat transfer divided by the temperature for delta S. So how can I use this to do for other things? Well, we have a thermodynamic property relation. We're going to be talking a lot more about this in a future module. But basically, if we start with the first law neglecting potential and kinetic energy, we end up with dq equals du plus dw. Now, if I have a reversible process, the work change is pdv. If I have a reversible process, the heat transfer change is tds. And so we end up with tds equals du plus pdv. Or we can rearrange that to du equals. Now we also can write this for h. Remember, u is h minus pv. If I take a differential of this, du is dh minus pdv minus vdp using the product rule. Well, okay, so du plus pdv minus a pdv, I end up with tds equals dh minus vdp. Now, these are going to be very significant for us later, but for now, they give us some guidance on how these variables are all related. So what does this have to do with a real process? Okay, well, a real process, number one, is not reversible, okay? But I took something that had the Q's and the work in there, and they were all path dependent, and I turned it into an expression totally independent of path. They are all process variables, just state variables. And so this is something that I can apply to any process, whether it's real, whether it's reversible. Now if I take this and solve it for ds, because again our focus in this lesson is how to calculate enthalpy changes, or entropy changes, the change in entropy is the change in H over temperature minus V over T times the change in pressure, or du over T plus P over T dV. So how can we do some calculations? Let's look at special cases. So first, solids and liquids. Okay, solids and liquids, I basically can say that dV is really close to 0. It's a very small contribution, especially in a solid. It's almost exactly 0. So that means that the change in S is really approximately du over T. Now du we've defined earlier as being Cv dt. And so this is Cv dt over T. Now for solids, and not quite so much, but almost for liquids, C sub V is going to be fairly constant. Okay, and it's approximately equal to C sub P. And so we can integrate this. And if the C sub V or C sub P is constant, I can bring it out of the integral, integrate dt over t, end up with the natural log of t from state 1 to state 2, I end up with the change in entropy is C sub P times the natural log of the ratio of T2 over T1. Now again, it's really critical that you remember that these units are based on thermodynamic temperature, which is absolute temperature. So I have to use kelvins or rankines whenever I'm doing these calculations. Now our other favorite special case is the ideal gas. Now, so the relationships that I know right now for an ideal gas are basically PV equals RT, du is CV dt, dH is CP dt. If I take those and substitute them into the expression for ds, okay, well I get du over T plus P over T dV. P over T, I can rearrange the ideal gas law. du is CV dt, and I end up with these expressions shown below here. So delta S is the change in CV over T dt plus R natural log of V2 over V1. Or if I integrate Cp over T dt, it's minus R ln of P2 over P1. This is, remember, representing a constant pressure process, so I need to add in a contribution for the pressure change. This is looking at a constant volume process, so this is adding in the contribution of the volume change. If the specific heats are constant for that ideal gas, so maybe I'm not talking about a really large temperature change, something like that, then I can integrate those first terms and get the ratios of C ln of the T ratio. So, what's going to happen to the entropy as I'm taking a control mass and looking at a real irreversible process? Now, Clausius's inequality can be manipulated and create a cycle, build a cycle of two processes. One piece, let it be reversible. The other piece, let it be irreversible. If you do that, there's just, this is a quick review. Delta S is always going to be positive, or not positive, greater than or equal to how the Q over T integral changes. Okay? So if I look at the net heat transfer divided by temperature, that is always going to be less than or equal to the delta S. It's going to be equal in the case of a reversible process. It's going to be greater than in the case of irreversible processes. If I ever end up with a case where I calculate delta S is less than the integral of dq over t, I know I have an impossible process. Now, entropy generation. When we looked at the second law, we were including an entropy generation term when we did the mathematical form in the previous module. And the reason we do that is because it's uncomfortable saying that, oh, the entropy change is always positive, okay, or greater than dq over t. That doesn't feel good to an engineer. We don't like just being greater than. We want things to be equal. That's kind of an accountant mentality, but that's how engineers like to do things. This is going to equal this. So I'm going to say, okay, dq is equal to tds if it's reversible, and if it's not reversible, well, it'll be a little more. Okay, well, that's not good. So what we do is we add or subtract, depending on exactly how we're using this equation, okay, a little piece to get them to balance. So if I have one piece bigger than the other, on the side that's smaller, just add a little something positive. Okay? And that's what we call entropy generation. In a reversible process, the entropy generation will be zero, but for others, entropy generation is always something positive. Okay? And we know that the heat transfer for real irreversible processes has to be less than the reversible heat transfer. And you put all these things together with the first law, and we find that the reverse or irreversible, the real power change, is PDV minus TdS generated. The irreversible or the real heat transfer is going to be something like the reversible heat transfer minus TdS generated. So I'm always going to have this little correction there for the amount of entropy being generated by those friction losses, the mixing, the unrestrained expansion, etc. So what does it mean? Well, okay. Entropy increases by transferring heat out of the system or by irreversibilities. The only way entropy can decrease is by heat transfer out of the system, but it's still limited by that Q over T ratio. Now, irreversible work is going to be less than reversible work, and reversible work I can get by doing the integral of PDV thing for a closed process. What that tells me is you always get less work than you hoped from an expansion process. If you think about the fact that the signs are different for work input and being smaller than a negative number means you have a larger value, then this also means that if I am putting work into a system, I really am going to have to put in more work than I thought necessary. Okay? For real processes, work is not the integral of PDV, and Q is not the integral of TdS. Those are only true statements for reversible processes. So, if you look at a PV curve, the area under that curve gives you the reversible work, but not the actual work. And the area under a curve on a TS plot would give you the reversible heat transfer, but not the actual heat transfer. So to summarize this portion of the lesson, let's review the various statements we have of the second law, because they all give us a different perspective on how thermodynamics impacts our understanding of the world. So we had the first one, the Clausius statement: we can't take energy from a cold object to a warm object without work input. And we had the Kelvin-Planck statement: we can't turn heat directly into work. So it's telling us our limitations. The next one also is a form of a limitation. It says the maximum value of the coefficient of performance or the thermal efficiency is going to be for a reversible cycle. Real cycles will always have lower performance. We know that the cycle integral of dq over t is always going to be less than or equal to 0 for a cycle, and ds is going to be greater than dq over t for a process. Or if you don't like the inequality, ds is dq over t plus this entropy generated. And we also can say that the total entropy change for the universe, for some process, is how much entropy change there is for the system plus however much there was to the surroundings. That will be 0 if it's a reversible process, and for the rest of the time, the real processes, this net change in entropy will always be positive. So we're going to pause there. We're going to come back with one more little lesson in this module, looking at performance of particular pieces of equipment.